In this paper, we examine the problem of tracking an unknown and dynamic number of moving targets using a team of mobile robots. There are many real-world situations where the exact number of target objects is unknown at the start of exploration, including disaster response, search and rescue, and traffic monitoring. In this paper, we examine the problem of tracking traffic using a team of fixed-wing aircraft. The target motion comes from a real-world dataset of taxi motion through downtown San Francisco. We used the GPS traces of over 400 taxis to create a data-driven motion model using Gaussian process regression. The resulting model for the taxi velocity is able to pick up on the street structure of the city. We also see that the covariance of the velocity is relatively low along the streets and high in the center of blocks where we do not get data. We also learn the statistics of the target appearance and disappearance as a function of position. As we expect, we see that a large number of taxis enter and leave the surveillance area along the interstates and the busy streets. In the lower right, we can see that the rate at which targets appear approximately follows a Poisson distribution. Using this motion model, we propose a novel formulation of the target tracking problem using the probability hypothesis density, or PhD filter, to simultaneously estimate the number of targets and their locations. The PhD filter accounts for false positive and false negative detections and measurement noise without the need to explicitly solve the data association problem. The PhD models the density of targets in the search space, and we represent it as a set of weighted particles, shown as the white dots in the video. For each test, we randomly draw 80 taxis from the test dataset, which are shown on the ground as the red, green, and blue coordinate frames. Note that not all taxis will be on the map at any given time. In the baseline tests, the robots follow the red lawnmower pattern shown in the video. The robots are equipped with downward-facing cameras, with the sensor footprint shown on the ground as the yellow rectangle. Robots following the lawnmower pattern are able to track the traffic but have relatively high uncertainty in the number of targets and their locations. To improve the results from this baseline, we use two different objective functions to select actions for each robot. The first is the mutual information between the future measurements of the robots and the target locations. At a high level, mutual information leads the robots to select actions that will maximize the decrease in uncertainty. Each robot has a set of candidate actions which are shown as the light blue lines. The robots can move up and down, left and right, and change their forward speed. Note that as the robots gain altitude, the probability of detecting a target decreases while the sensor footprint grows larger. Mutual information balances these two effects. Qualitatively, we can see that the robots using mutual information tend to circle around the environment and stay relatively low to the ground. This allows them to track the visible targets with higher precision than robots following the lawnmower pattern. The other objective function that we consider is to maximize the expected number of detections by the team. This also balances the size of the sensor footprint with the probability of detection, but favors a larger footprint than mutual information. With this and mutual information, the robots are planning for 2 time steps in a receding horizon fashion. This means that the robots plan for 2 actions, execute 1, and replan using the new information. This offers a significant advantage over planning for a single time step. Also, the team selects actions using a greedy assignment policy that scales linearly with the size of the team. This policy is guaranteed to yield action assignments that are within a factor of 2 of the optimal assignment for any submodular function, including mutual information and the expected number of detections. Qualitatively, we see that robots using this objective fly at a higher elevation to increase the size of the sensor footprint. For this traffic monitoring task, this results in the robots tracking a significantly higher fraction of the targets with lower uncertainty than robots using either of the previous objectives.